Last time what I did, I uploaded the last video we had that Kenya recorded, and what I did was to remove any possible identification of your names or something from the screen. So it was just a cropped uh, part of the video, so you're not going to see. So it's just the material at hand, so nothing else. Good. So today we're going to talk about failure theories. I believe it's going to be a shorter session today. This is very interesting because in the first lecture we saw stress. So how stresses are, let's say, developed inside of any element or any material, or any steel material or any other material, but how stresses are developed. And we talked about, okay, if you have, I'm going to start drawing here, but if you have, for example, forces, values for that, I'm using this integration term, or yeah, develop or transform into stresses, machine, because just remember, perfect. And then on the other hand, we're having the middle something that is called the material properties, let's put the material, but this is according to the constitutive, let's say, law. And then, that changes, that's going to, let's say, transfer everything what's happening in this side to what is this strains. And that's a brief recap of what we have seen. And then this is deformation. Great. And then that these two things here, that one of the most popular, let's say, laws that we can use is Hooke's law. And by the way, I need to apologize because in the previous sessions, many times I have written Hooke's last name really bad. So I just misspelled it. So, okay. Then the idea with all of this is kind of top by this. So what you have here in this case, I believe my cursor can be seen here. So in this case, this seems to be some sort of crankshaft from a car. And then, it broke. It just broke. Why broke? Well, that's another question, but but it broke. This is a crankshaft. Yeah. Then, it broke in a very, let's say, distinctive way. When you move to this side, so this is a gear from a gearbox. So these are the teeth of the gear. So this is one, two, this of that. But then there's one missing here. It broke also. Why broke? That's another question to be answered by the people who operates or is in charge of this type of machines. But it broke. No, it broke. And when you have, and this one here is some sort of, let's say, that crane. Yeah, let's put it beam. I don't want to call it crane because it's not, but it's just a beam that they would try to lift this. I believe this is some sort of machine tool that they wanted to lift, and it just failed. So it couldn't handle the forces. So it shows this just when just didn't hold to that. And again, what we want to do is that we want to in a very simple way at this level is kind of what we have shown before is that why it failed, why it breaks and why deforms beyond usable range. And today what we're going to be tackling is this part of the answer to this question: why does solid material fail? Of course, you have many other type of failures that you could add to this list, that we are not taking into consideration, such as some kind of surface failures due to failure, or you cannot just work with a gear because the surface was uh, so worn out that it just it cannot do the work. But in a simplistic terms, what we're addressing in this course are these two possible answers to the question, and because it breaks or because it deforms. And you see, for example, in the content of the lecture that we are dealing with stresses and and these failure theories, and also we are going to be dealing with how to calculate deformation in beams and axes. So this is important that we are trying to answer to these two questions. Then today we're going to deal with this because it breaks because it just the material couldn't hold the forces applied to it. So, and then to know what was happening there, so we need to know what type of criteria should we use to determine before it happens, of course, that this is going to break, this is not going to hold. So we cannot do it in this way, or we need to modify characteristics of our materials. Remember that as mechanical engineers or as engineers, specifically for this purpose, a design is a combination of three things. So the first one is going to be kind of the loads or forces applied. Let's call it forces applied, and let's assume that forces include everything, such as point forces, body forces, moments, torque, everything. So you're going to have forces. So the triad that you're going to have are forces applied. Then you're going to have the geometry of the material. So that's going to be a second component that of vital importance in this. And then you're going to have the material. It's kind of one of the pictures I had in the first lecture. This triad is the most basic triad not considering that you are designing anything related to corrosive environment or extreme cold, freezing conditions in the Arctic or anything like that, or materials that are going to be working in you know in an electric arc furnace or close to it where temperatures can be really high. So when we talk about really simple, a simplistic approach to design, we need to manage this triad. In this triad, forces are something that you might not be able to change because those are the forces that the part needs to resist, the machine element needs to work with. So maybe there is no change here. So this is something prescribed that is called, so it's already existing. Because somebody, when they ask you, hey, can you design this kind of part? As okay, so you start searching for, okay, what are the loads that are going to be applied there? What are the forces that I need to, the parts need to withstand? So you take that as an input, as a very fixed input that is most likely that you are not going to be able to change, but you have to be say conscious that they might be more deleterious or damaging than you are considering. So you always have to think the worst when talking about forces. Then these two things here in the bottom is what is left to you. So your creativity to select the shape, the geometry of that, and this can be one of the most difficult tasks, because if you're designing something that is not existing, or that you don't have anything that you can take as a baseline and modify it and use it. So this can be very complex because it requires a lot of imagination on how to have a geometry that could possibly hold or withstand the forces and could also be functional. And not only that, that would be resistant and be functional, but be beautiful. So nobody wants to have an ugly looking machine or ugly looking part, even though it makes a job. So the best condition is that the geometry is very, let's say, appealing to the person, to the people using that, let's say, machine part. So you would say, but come on, but if it does the job, and let's say, yeah, but nobody wants to drive an ugly car. Well, I'm talking about, majority of people. Nobody wants to live in a very ugly, represented house or something like that. Well, excluding, certain unfortunate conditions, but I believe you get the idea about what I'm saying. That this might be one of the most complex tasks that you might have in front of you when designing things. And why is that? Because if you talk about material, you know what? Materials always rely on what's the type of application, and most of applications have been done, have been tested. Barely newer applications are going to come out. So you might have a good reference about which type of materials to use when dealing with certain, let's say, cases. You can ask the material providers, hey, I have this case, I'm trying to design this, and these are the conditions, and those people selling materials, steels, or any other material you are using for your design, they're going to say, I recommend you this. It's the same case that, you as an engineer, you're going to design such a gearbox. So this gearbox here, if I draw in this part, this is the shaft, and there is a bearing here installed here, a rolling bearing. So then you have this bearing here. If you don't have an idea what type of bearing you need to use here, so you just call the bearing manufacturer. You just call FAG, SKF, sorry, or FAG or any other. And then Tinkham, I believe is teaming. I need to check this, but I believe it's written with M. And then you say, hey, do you have this application? Could you recommend, this type, which family of bearing, what type of bearing should I use? In terms of bearings, there are many possible, let's say, models to choose from. If it's greased, not greased, if it's working with oil or not oil, if it had some guards here or doesn't have any guards, if the material of the cages, is overwhelming. And if such overwhelming that you don't need to be an expert, but you need to rely on people that manufacture them or design them, and say, talk to the person, SKF, say, I have this application, and then what you recommend, and then they would tell you, okay, for this type of application, usually it's this. For the case of material, there is kind of there are even charts that you can use that they tell you kind of ranges or big ranges of application. And then, it's going to say, okay, what's some kind of a diameter related to strengths, or something like that. And then depending on the type of, or velocity, inclusive of operation, you would just look, okay, what are the values of that? And then it would say, okay, I recommend you to use, for example, well, this is an North American nomenclature, so C45, something like that. For your application, we recommend this. Boom, and then you use it back there. Actually, the name of this chart, I always forget. Just uh, they're called, well, ABIs or RB or something like that. I don't recall exactly the name, but it's just a chart that you just search for it, and it would tell you, well, we recommend you to use this because it would consider weight, it would consider kind of the strength of the material and all of that. So in a very simplistic way, you have this. So uh, um, that's it. No more than that in that sense. What questions do you have so far? Great, so let's continue then. Most of the things, when we're here and you say, okay, I want to take care of forces and material and geometry. So what are the, what's going to tell me what's happening? I know that because of the forces and the geometry of this part here, I'm going to have a relation. Well, I'm going to have stresses. Yeah. And then it might be possible then between the geometry and the material, I'm going to have something represented in terms of strength. Actually, this is more of the material side than from the geometry because, but I'm putting geometry here because strength is calculated based on certain parameters there. Then what you do is, well, I know that there are some stresses being created, and then there is something within the material that might be opposing to the stresses, and that's the strength, which is another form of their, let's say, phenomena of the same type. So stresses are pressure, so to put it that way. So what we need to do is compare what's happening with this with what's my capability. So what's being caused by the forces, if that's going to be larger than what I'm able to withstand. So, but then we need to know this. We need to know what is the strength. So what's available? How much is it? So I know that I can compare this because I calculate, stresses from forces and geometry. But what's the value I need to compare with? So this is where this other slide came in. You say, well, there is often this type of tests. In this time, well, this is a tensile test. This is a very popular test. I believe you have seen it already. That you have a specimen here in this part, and then you have something pulling this up that is going to try to stretch this part here or this part here. And you're going to have a load cell, meaning an instrument that is going to measure how much force is applied. And also you're going to have another type of instrument that is going to measure the, let's say, the deformation of the part, meaning the elongation. So two instruments. Two instruments are going to be used to calculate. The first one, force, is going to be used to calculate stresses here, and the second one is going to be used to calculate strain. So I use strain because you need to know section, for example, in that sense. So when you start applying force there, you're going to try to start elongating this part, and then this is the first one, original specimen that you use to start the test, and then this is going to be the final when the test ends when there's a fracture in the piece, or the fracture when the piece breaks. So as soon as it breaks, so the test ends. This is all everything automatic. So you just position the specimen in the machine and then push a button, and then these sensors are transmitting the information to computers, and that's going to make you say have that. Any questions? Great. Then you see that if this is a similar specimen, this is going to be, look at the difference in length that the specimen ended with. Kind of, it started here and then it elongated this much and then it fractured. But this is not only what is interesting from this part. The part is that this falls into the phenomenological approach. Where we're trying to determine what's the behavior of the material by looking from outside. It's kind of looking, what's happening within the house from the outer window, kind of looking, peeping at the window, saying, oh, what's happening inside? So this is what we're doing here. And the situation is that, by having these two sensors, we can draw this curve. I'm going to put it a bit bigger, move this up. I can. So you see that here you have kind of a material evidently that behave according to Hooke's law. And you're going to have the straight section of the curve, meaning that there is a proportional response between the force applied to the part and the elongation that the part is going to have. So this is let's say, this is the proportional part. And in this proportional part, as you know, this is the elastic deformation. And I would like to repeat this, even though you have seen this, because this is a very interesting thing I'm going to end up saying later that you might have seen, but if not, you're going to be surprised. Then you have the point where, that proportionality breaks because the material already doesn't behave, elastically, and starts what is called a plastic deformation until it breaks here. Yeah. This is a representation, but usually this curve is something like, goes more flatter or something like that. But this point here is that's something that is going to allow us to compare what is the loading case of my part with the question of, is the part going to break or is it going to deform? And this is called the yield strength. Yeah. And this is used in many of the formulae that you are going to see in engineering in your course. Other important part is like, this one, or this one, this is ultimate strength, and then this is fracture strength, kind of something like this is used for fatigue at some point, or both two are used for fatigue. And no, not much, yield strength in certain theories. That the question now that we need to ask ourselves as engineers is, okay, which value do I use to be able to determine if these stresses are larger than the strength, or no, there is no breakage going to happen there. Before I jump into the other slide, uh, because we're going to deviate a little bit from this, what questions do you have? Good. So when we're designing things, when we're designing machine elements, for sure, I know the loads. I have imagined a very nice geometry that is not heavy and is, good looking. Let's put it in the way, and it does the job. So what's kind of the comparison yield strengths that I should use if I have selected certain material? So I have here a table for well, this is one of the easiest one to find. A 1020 steel is yeah, it's plain steel, very popular within users in the mechanical industry or machine industry. And you've seen this also. Or if I have as a question, let's try to use this, what is it? React React button and see how many of you have seen this type of tables before. Could you please use the React button in the bar to say, yeah, I've seen it. Yeah, I have one. All right, great, great, thanks. Then you said we usually use this type of this number here, which is the yield strength or tensile strength, or yield strength. Yeah, yeah. And you say, well, if I want to know, this is where things get tricky, and this is something that I would like to, let's say, share with you as an engineer in terms of design. Yeah, okay, 300 megapascals. So that's it. That's the point. That's the value I need to take into account. Take it, then and then imagine that according to the forces applied to the part, your, let's say, is 300 megapascals. This is the, let's say, the stress created by the loads or the forces applied to the machine. When you compare these two, oh, definitely it's going to withstand because 300, 350. So good. Yeah, let's move on. That's it. Now the question is how this number was produced. So how these guys that are selling this steel cold rolled, a 1020 steel produces came up with this 350. Well, yeah, they came up using this, let's say, test, because this is the way they produce it. Okay, but it was one test, two tests, three tests, 1,000 tests, a million tests. So how many? And then you would say, well, that's a good question. Yeah, well, maybe several tests. They did test it several times, and they got different numbers. So they got, let me bring here. So in the tensile test, so they started testing, trying to keep the same controlled conditions for each one of the tests. For example, when you see those tables, they would say, okay, this value of 350 megapascals was produced by using this type of specimen at 21 Celsius degrees laboratory with this much humidity and this machine and so on. So in the tensile test, they're going to get values for that. Let me bring this. So they're going to say, well, the first one was 300. So the first test, let's put it in this way, it was just 300 megapascals. Okay. The second test, 310 megapascals. The third, 400, and so on. The end test, I don't know, 1,000 tests, it was, I don't know, 370 megapascals. What do you think they did then to produce these 350 megapascals? Well, one of the most obvious answers to that is, well, what we do, I cannot represent this, but I can present you with the average of this. And then you use it. But if we at this point, you guys as engineers, you start seeing this, you say, hey, wait a second. So uh, you had a specimen that tested 300 megapascals, and but another that tested 400 megapascals. So which, if I buy material, this material from you, which one I'm getting? The 300 version, the 400 version, the 310 version? So which one I'm getting? So what's happening here? So now things starts getting tricky if you are very, if you start scrutinizing your ways of designing machine elements. So, oh my goodness, yeah, wait a second. So it means that if this goes up, if I by any bad luck I got the 300 megapascals material, and then my load is 310 megapascal. Look at this. Then it means that this is going to fail. So what should I do? And let me put you the problem from another perspective. When you calculate forces and they say it's 300 megapascals, are you really sure are 300 megapascals? They're just, yeah, well, yes, that's a calculation you got, but it doesn't mean that you are error. You're just creating a big problem because you are using very wrongful assumptions, or you are just not considering things to go over certain values because you are assuming things. So it gets tricky. It gets complicated. So coming from a very simplistic triad that we have used to, okay, just calculate forces and then design a geometry, select a material, and that's it. Boom, you have that. We found out that, oh my goodness, so would it fail? Well, I don't know yet. So I want to throw out this question to you guys. So what should we do now? Question to you guys. So any one of you who wants to participate and just throw a comment or a thought, how should we tackle this? Anyone interested in sharing their thoughts? Nope. Okay. So I continue with the monologue. Good. So I said, well, okay. Well, maybe we shouldn't take a discrete value to calculate this. So if I know that this is going to be a variation of many values, so this is a variation, and this might be a variation also, meaning that they vary, tremendously within certain ranges. Then I could then take it as a hint that I used the average. An average is a statistical figure. Statistical measure. Okay, let's see what statistics say. Statistics, and then if you move back a little bit, is okay. Well, no, or you move forward. Okay, probabilistic. What's the probability? Because now that question was very clear in the sense, oh, am I sure that am I getting the 300 megapascals or the 400 megapascals? And that's where there's a probability of getting 300 or 400 or something. So there is one of the ways to deal with this problem, which is the probabilistic considerations, meaning that if this curve here is the stresses and this curve here is the strength, and yet, guys, we haven't entered into what are failure theories. So I could have come directly to tell you what are the failure theories and how to apply it, but yet, this is very interesting because this is kind of the, the opening of all this subject. Then, yes, you have the stress curve, meaning that, again, we are assuming that any of these stresses that are going to be applied to my part and any of the strength determined by this tensile test are going to fall into or can be described as a normal distribution, like you have it here, kind of a Gaussian distribution. And it's like, okay, if we consider that those values can be described by a normal distribution, then the question would be, what is the probability that there is the strength of what I have is the same as the stress that is imposed on the part. So basically, if this is just for reference, formula for reference is not going to be used in any other place of the course, but just here, but it's for your reference. So basically, this is a simultaneous reference of one phenomena happening, two phenomena happening at the same time, that sense, or simultaneously. Then they go, okay, that's fine. So conditional probability. And then the question is about now, what is the probability that the strength is less than the stress? Because that's going to mean that something's going to fail if the strength is less than failure. So it cannot be taken discretely, but has to be taken probabilistically. So when you have this formula here, you say, okay, the probability of that the strength is less than certain value of stress is mentioned here. But in definitive, when I try to investigate over the whole range of phenomena here, so what's the probability that that the strength is less than the stress, and is represented here by this kind of integration term. So what's the probability when the whole phenomenon goes from a equals 0 here till infinity? That's an 8. And then what's the probability that the strength is less than the value? So meaning that this small differential region is closer to 0 than this one. This changes the whole paradigm on how to calculate things. So we went from the simplistic, yeah, if it's less than 350 megapascal, just go for it. But now it's like, what is the probability that it's going to be less than that? And this is a way to do it. However, this is very complex. And from a engineering point of view, in the day-to-day things, kind of normal quote unquote things that we are going to be facing, such as an industry that design this, design that, not for newly, let's say, designs that require deep study before launching that design. So this might not be the answer to this, because it's pretty complex, because you need to understand what are these stress curves, and then after you find out from material, and you build these curves kind of here, the strength, and then you build this curve for the stress, and then you find that the distribution, the density function of these curves, and then blah, 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 do everything, then you can propose this formula. But if not, it's going to be complex. There is another method that is called the semi probabilistic consideration, and also a third method that you might be very familiar with, which is the safety factor method. And the safety factor method means, whatever value you have, multiplied by 2, by 4, by 10, and that's going to be your value. And that's it. And you can call it a day. But in this sense, what you do is that you say, okay, still with the semi-probabilistic consideration, you need to know more or less information about, the curve that is forming the stress and the curve that is forming the strength. And what you do is that with the stress, you take the upper quartile here. This is then of the extreme upper that you're going to have, from here to here, the upper quartile. I believe this is Q3 after Q3. And then for the strength, you take the first quartile, the smallest one. And as long as this value do not meet, it is said that you're safe to go. And the difference between the semi-probabilistic method and this method here is that you don't do any kind of complex calculation. But in this case, what you do is that you just make sure that analyzing the quartiles of the probability function, that you know what, this is going to, well, the maximum is in this range and the minimum is in this range. So let's make them not meet, that they don't meet in the middle. So, and we're fine with that. It is said, when we come back to again to the safety factor, that this is something that is kind of the use of safety factor is being little by little abandoned by semi-probabilistic methods and by newer tools, software or design tools, because we can get much better approximation with newest design tools that they are awesome. They are really quite awesome. But in this case, well, this is a very good information I'm giving you here. Funny thing is that when you say, okay, I want to design something, I want to come back here, I want to have forces, I want to plan a geometry, I want to select a material, let me use my creativity as an engineer to design this part. If that what you're designing for falls into a group of very well-known things in use by humanity, you might be ending up using standards. This is an extract from a German standard for bridge and granty cranes. So bridge cranes are those, for example, if you have some sort of deposit or company. And then a gantry crane, well, gantry is different, but a bridge crane, you have a beam here, and then you have a beam in the other side. Then what you have here is, change this color to black momentarily to this one, is that you have something here. You have a structure here from this one to this one, where is a crane, and this crane has a hook. And this, sorry, and this crane can move, from one side to the other. It's hanging kind of, this could be, I don't know, it could be 20 meters, it could be 50 meters, depending on the application, easily. And then this is hanging, and then the length of this, the width of this, well, it also can be, very ample here. So when you have this and somebody, you're working with this, and I had the chance, I have never, well, theoretically, my graduation work, not thesis work or something work, was designing this kind of the whole structure, and also plus the kind of something to support the crane. But it was very interesting because still to this day, people who designs cranes, even though they try to use a software, they have the standards. And these standards tells you everything there is to know to design such equipment. So you don't have to be inventing on, oh, what's the geometry? Oh, what's the material that I should use here? Or, hey, what are the forces applied here? Because the standards give you everything. So as an example here, stress equation, look at this. Of course, this is out of context in the sense that we don't have any context to relate to say, this is a stress for something, but they're giving you the formulas that you should use to calculate, stresses happening within the crane. And they give you the coefficients, they give you limits, they give you all of that. They give you indications about how things should be positioned or considered. So if you follow these standards or any standards kind of similar to these, to design things that are very well known by humanity, so uh, this end stop, this whatever I'm going to say next is irrelevant because everything is contained in the standard. So we are not that free, after all, to design things when it relates or with regards to things or machines that are very well known. Of course, if you're going to be a tremendous modification here in the way you operate, then you say, oh, yeah, well, it's going to be like this because, I have the standards, but then I have to do extra experimentation on this. And let's remember, standard data. So this comes from years and years of results, experiments, failures, experts, comments, or let's say theories. So everything is enclosed and customized to have it here in the standard. So that's it. These are your boundaries. The standards are your boundaries, and then you follow them. And if this crane fails because it breaks down and falls and injures somebody, one of the questions they're going to ask is, how was the follow-up of the standards when designing this? And if you are off the standards or out of the standards in certain ways, so that's no, that's not good. That could be very negative in that sense. What questions do you have so far? Let's continue. Coming to the real world now. Well, I don't know the academics world. In this sense, this is the real world, so academics world. To understand how stresses are formed, we saw kind of state of stress, how the relation, how they're formed, how they're calculated, all of that. But the question was, okay, how should I come from forces to stresses? And I took these images from this website. So shout out to this person, the person who wrote this website. I didn't find the name, but referencing that because it was very nice, to have that. And you say, well, depending on the type of force you have, you're going to have different stresses appearing in the part, in the steel, on the body, on the element you are designing. Typical compression and tension. Let's call the yin and yang of this type of force. You have bending that we're saying we're shearing or shear and torsion. Those are the most, let's say, those are the ones which we're going to use in this course. So whenever you see a free body diagram of an element, you should be able to identify right away, okay, this force causes this type of stress, or this torsional moment causes this type of stress. And again, as a reference, well, if I have tension or even compression, that's going to produce a normal stress. If you have, a shear, which basically is that, that's something that is lateral to, this is supposed to have certain, let's say, weight coming down, and then these two forces applied at the top. So that's going to cause shear on the part. And if I have bending, well, bending is going to cause it's going to induce on the part normal stresses. And if I have torsion, so this is going to induce shear stresses. And this is a very nice figure about why torsion is something like this. So look at this. So this is the undeformed part. And then when you apply torsion, what happens in a kind of an element here, a surface element here, is that you're going to say, I don't know if the word is induced, but you're going to cause shear in that element, the parts of that element. So this is pretty easy to see, easy to grasp, and to understand that different types of forces or of loading cause different types of stresses. And in this sense, in these four cases, we're talking about normal and shear stresses. So definitely that is totally aligned with, see if I can, with if I take a planar representation here, this is going to generate or create on my part, well, you're going to have normal stresses. Of course, these ones, and then, well, you can continue here if you want sigma something, let's put it's x, xy, and so on. X, y, and so on. Well, so on ended up. because the idea is to come from forces, loads applied to the part to the stress tensor, and then from the stress tensor to principal stresses, and then from principal stresses to verification if that principal stress is going to, let's say, according to certain arrangement called failure theories, is going to, let's say, indicate that the part is going to fail or not. And that's kind of the way to go. Kind of, you have loads that, that's going to create stresses that we're going to represent in the tensors, stress tensor. Then that's going to be up under a failure theory, or let's put it in a way, kind of principal stresses, and then failure theory. And if you see, this is sort of the resolution process of any of these problems. Give me the loads, let me calculate the stress tensor, let me know what are the principal stresses, let me apply a suitable failure theory, and boom, still you're going to find in books, they're going to ask, okay, what's the safety factor that's giving you? And then if it's larger than 1 or larger than some prescribed stress factor, safety factor, then it's okay. If not, well, it's bad. And then still, even though I mentioned up here that safety factor is is kind of becoming not the standard to do it, but still we are using safety factors. This is a solution process. If you ask me, okay, how should I solve this problem? Well, here you go. This is the way you should do it. Pretty straightforward. All right. So these are a couple of examples. For example, kind of a couple of examples. Imagine that you have a round bar, and that's subjected to a traction force, 50 kilonewtons, to have a bending moment, and you have a torque. And then the question is, okay, what's actually this is a pretty, what's the loads? Okay, question is, okay, what are the stresses? How can I construct the stress tensor? Okay, now if I would tell you, okay, now you have this, now give me a stress tensor, or please construct the stress tensor, the very first words that should come out of your mouth is where. Because just remember, stress tensor, it doesn't matter how you orient it, within, if you have a stress tensor and you orient it differently, the invariants are going to be the same, and then you have only one set of principal stresses, and that's it. But if you move that point of a point where you are calculating the stress tensor 1 micrometer, well, that's an exaggeration, something to the left or to the right or up and down, the whole stress tensor changes. So the first question that should be asked is, okay, where? Would it be, sure, so would it be here, or here, or here, or here, or here? So which one would be the point that you should use to, you better choose to calculate the stress tensor under these loading conditions? So now my question to you guys, if you had to design this part, so what would be that point that you would choose to say, okay, I'm going to take this point as a reference to calculate stress tensor and to see if this loading condition is not going to exceed the strength of the material. So question to you guys, which point would you choose in this round bar as a point to design this element or to calculate the stress tensor? Nobody?
Maybe the part where it's most likely to break, so near the wall.
Okay, that's a good start. So we're talking about somewhere in the vicinity of this. Okay, where?
On the top or on the bottom, like take the worst possible case.
And for you, which one would be?
So either the top or the bottom, like
Perfect.
we can take the top.
That's correct. For the way this is loaded, kind of if you take the top of the bottom, is going to be pretty much the same, different signs, but it's going to be pretty much the same in magnitude. But yes, it's something like this, it's kind of the top of the bottom, in the sense that, hey, let me check this one here. They said, because this thing might fail here, because with this moment, and it's kind of obvious in the sense, and now we are choosing a point, to an infinitesimal point, to calculate the stress tensor. And you know what, guys? This is what finite element softwares do. So pretty much you've seen that, or you've taken some type of courses regarding finite element analysis. And what it is done is, let me pick a color here, maybe this one here, and they just divide this into many points. And they start asking, okay, what's the stress tensor here? What's the stress tensor here? And so on. So this software start calculating the stress tensor in all of these parts. And not only that, they also start uh, kind of thinking, not thinking, but proposing, depending on the methodology or theory you are using, on how the stress, because yes, I know that the stress here I can calculate it, the stress here I can calculate it, but no, this is a discrete, what would be the word, the pronunciation correct, discretization or something, making it discrete, let's put it this way. Yeah, I selected this point, this point, this point, this point, this point, but I'm missing this point in the middle here. So am I missing something important? So the software, what it does, it creates certain functions to try to estimate what's happening between points. Yeah. So you don't end up with a, let's say, total discrete element, but on some sort of, let's say, continuous element. This is what this, let's say, software do, but they do it 100,000 times. Remember 10 years back when ANSYS released something like they reached about 1 million points. They meshed, because this is called meshing, but they divide the part into with a mesh. It could be a two-dimensional or three-dimensional or unidimensional mesh. And so we reached 1,000 points in the mesh, 1 million points in the mesh. So I believe they're way far right now. But then these functions here are also telling you something. So imagine how heavy those software work. And here we're just asking one question. So okay, what's here? This is the most critical one. Yeah, that's understandable. That's a very good observation. Yeah, that's the one. Change colors again. Good. Then if I extract this element and I build some sort of, let's say, infinitesimal cube there. This is in point P. So I could start populating, let's say, this example. So I could say, all right, so let's imagine that this is in the x direction, and so on, and this is in the y direction. So which will make sense to do this like this, because let's keep it two-dimensional. Let me try it nicer. Yeah. So this is it's not a stress tensor, well, part of the stress tensor, but it's in two dimensions here. So okay, now I know that I'm going to have normal stresses in here. And it's going to be the same as this one, normal stress. I'm going to have probably normal stresses here. I'm just assuming the direction. I'm going to have also shear stresses. And then just to write it once, because there's no point writing the name four times. This should be to keep consistency with the reciprocity of shearing stress. So this should be like that. Then the question is, okay, now guys, how can I come from this part to this part here? You say, oh, okay. So let's take this load here. This load is producing tension on the element, meaning that it's producing a normal stress. Now, this is important now, guys. One question to you, and let me know, please. If you guys are very clear, crystal clear with what I'm doing right now, because you've seen it before, let me know so we can move forward. Just let me know, or right now, for sure. If you said, no, we've seen it and we're pretty clear with that, so we don't invest time in this part.
So clear, you mean by how meshing is done and how it's distributed, or?
How to come from loading to the stress sensor. Basically, how to, let's say, translate loading cases into stresses in the stress sensor.
I mean, it's. I think we discussed this in the previous lecture a bit as well, but I think if into words you can explain it, and then we can move forward. At least for me, I don't know how about the others.
Yeah, thank you. So what about the others, if you're there?
I think we could use a recap.
Sorry?
I think that we could use a recap.
Okay. Yeah, I won't go into the calculation itself, but it's very intuitive here. So I know that this force is in tension, and that's going to cause a normal stress where, well, in the direction where this load is applied, so in the x direction. So one of the components that I'm going to have here as a normal stress is going to be caused by the tension of this force here. So basically, it's going to be this 50 kilonewtons divided by the area of the bar. Let's put it that way. And definitely, this is also going to appear here. Great. And if you want to make it more, let's say, suitable, you know that the area of the bar can be characterized or calculated as this one here. So you have the diameter, so everything is given. Now let's put it once. As there is just one radius, so there is no need to specify anything. Great. And that's it. That's the only thing this load or this force imposes or creates a stress in the part. Let's look at the torsion maybe. So we know that torsion produces a shear stress. Now, as I'm looking this from the top, yeah, it is clear, and according to this figure here, because it's exactly the same, that the torsion created in the element due to the torque applied, well, the stress, shear stress created on the element, thanks to the torsion or torque applied to the piece, the element is going to be in this way, in this form. If I take this to this part here, and I'm looking this from the top, well, this then would be Z, basically, isn't it? This one here is going to be, actually, I'm going to write like right here, the resultant of the torque, which is that, let me write all complete. Is 30 kilonewtons meter divided by J, which is the polar moment of inertia. And you can find this J, this is a pretty common section, P d4 divided by 32. J, and then that's multiplied for C, which is the distance from the neutral axis, that in this case coincide with the centroidal axis, to the point of, or the point of analysis in this, which is going to be half pi, I believe so. Yeah, half diameter, or the radius. And that's it. Then you have the bending moment. Bending moment is going to produce on the part, in the part, kind of this normal stress. And where? Well, I know that if I split this with a line, let's use the screen one. Yeah. Here. Oh, actually, we know the stresses are going to be split by the neutral axis. It's going to be something like this. Then you're going to have here tension on the top, and here you're going to have compression. And having that, then it means that in this part where I am kind of considering the point of study, to see if this is going to fit or not, then this is going to add up to this normal stress represented here in the x direction. So I need to add this typical formula for bending, which is the moment. This much, and then this multiplied again by the radius, and then by I, the moment of inertia of the section, and then that moment of inertia is kind of very close to this one. It just changes by kind of this 464. And then that adds up here. And there you go. So now you have what are the values of all of these shapes, of kind of the translated values of these. Of this loading condition into this. Now you have this. you have how much is it? Well, this is nothing at the moment because of the point selected. And then you can, let's say, follow from there, meaning you have now what is the calculate the principal stresses, and then follow with the whole procedure I showed later. Questions? So, let's say a three-dimensional case. So this might be, well, this is a bar, but it might be a piping or something, and there is a force oriented in this, let's say, in this direction that is kind of more explained here, meaning that there is a force, and the force forms an angle with each one of the Cartesian or the coordinate axis. And then well, yeah, we saw that you can represent the orientation of a vector using direction cosines. And then, okay, we are using angles on here. This is the definition of using direction cosines. And then, okay, but you're not giving me this angle here. So what's happening there? Well, we know that if we use direction cosines, the three angles are bounded by a law, by a constraint. And that means that we know that if I have the L, this three direction cosines, L squared plus M squared plus N squared, that always have to be equal to 1. Meaning that if I have two of those, I can calculate the third one. Yeah. So I don't need to explicitly say everything. Okay, of course, I need to calculate it, but it's not that bad. Then what you do definitely is, if you take, for example, this is L, this is M, and this is N, then you say, all right, so I don't know L squared, but this has to be kind of multiplied by cosine of 30 square, or well, added the cosine square that's equal to 1. And then just find your, actually, and then this other one, or twice you can put it in there. And then you got it. But then that's not the important thing, because when you're doing this is because it's very tricky to work with any vector that is oriented differently than those from the Cartesian axis. And then what we want to do actually is say, hey, why don't you tell me what are the components of this vector along the Cartesian axis? And we're going to have something like this. So I'm going to have, okay, this is one component, fx, and then you have this component here, fy, and then you have the z component. Why would you like to do that? Well, because if I start working, if I select this force here, I know that this component is here. And again, similar to this case, it's pretty much obvious that the point of interest I should be putting let's say my attention on is somewhere in the vicinity of the joint of this bended bar to the wall. And then again, you can take, the upper point or the lower point, and then of course there's going to be a difference, but no, let's take one of the points. So let's take the upper one. And you say, okay, I selected the point where I want to, let's say, determine what's the stress tensor here. I have one force, Fx, which is one component of the total force applied to the specimen, to the bar. What type of forces, what type of stresses creates on this element? Hey, and now I'm really going to have a three-dimensional stress tensor. This is the point P. So, oh, okay, so this force is creating two things, two stresses into this point here. So first, this point I could consider, or this force, I could consider it as a, let's say, a consequence of having a force here and translating this force up to here. Yeah. So this means that this force can be substituted in this point by a force and a moment. Okay. Where the force is going to be the same force, Fx, and the moment is going to be Fx times this distance. Or if we wanted to write it better, it's going to be that moment is going to equal 300 times Fx. And I can say, well, okay, I want to work with this. And now I am in the very same case as before. The force and the moment, bending moment. And that's going to induce here a couple of stresses here. One stress, thanks to the Fx, let's put it that way, plus one stress related to mx, let's call it mx, to keep track of that. Same here. Questions? What question do you have so far? All right. Let's say this force, this y, Fy. So it's like having it here. Drawing. So this force here is kind of the application of first, I could have a force here. It doesn't change because I can translate the forces as, they're free vectors. I can translate them in the same axis. So let's put it like this. So and also I could kind of move this one to this one, and I can transform this into a force and a moment. Yeah. Then what stresses are this Fy force causing on this point of interest? Well, I have a bending moment. This is obvious because if I pull this bar and I pull it up, this is going to cause a moment here. So this is going to induce also a moment, around this point here. And actually that moment is very well aligned with this mx moment. So it means that this moment created by translating this force from this point to this point is going to produce, or going to add up here, a normal stress in that direction, all there. However, the force itself is something that is very similar to what's happening here. So it's creating a shear stress in that section, meaning that shear stress where? So I know from this part is creating a shear stress on the section lateral to that, lateral section to that. So meaning that the shear stress is going to be using the same color here. Now, we call this, if I take this reference system, xy, so 2Fy divided by the area of the bar. I'm not going to write the one in the other side because it's obvious by the reciprocity of shear stress that is happening there. And that's it. Now what's happening with the component in the z direction? Now, Fz. So Fz, z, so it's something here. Again, I can translate it here, and then I can translate it here. So this is going to produce Fz plus a torque around this section. So this force here, which is the easiest to tackle, is going to produce, again, a shear stress here. And this torque is going to produce a shear stress also kind of aligned with this section. So meaning that is very same aligned with this section that it is producing this force here, this shear stress here. So, and that's going to be brought by the torque times C divided by J. And there you go. So it's a very nice, let's say, process. It takes time, but definitely this is something that you might have to do to get to this point to say, okay, how's the situation here? Well, it is like that. Definitely this is also repeating here and so on. Good. Now let's go to the topic of the class. When we talk about failure theories, we need to ask, okay, you want to talk about failure theories, but where, what type of material? So in this course, we're dealing only with steel most of the time. We can have some type of problems with wood and stuff, but they are not the main topic of the course. In this case, we're talking about steel. And when we talk about steel, the question is, okay, you want to talk about failure theories? You want to talk about failure theories regarding steel? My question to you is steel ductile or fragile? So they say, oh, okay, what does it matter? Well, is it ductile or fragile? Fragile. Well, we need to switch just a little bit because every day you learn something new. Just a second. fragile or fragile. If there are any native speaking, English speaking, so just trying to find out the fragile. Well, let's stick to fragile. If it sounds bad, just let me know.
I think it's brittle.
Brittle, yeah. That's yeah, brittle, yeah. Yeah, but it's related to fragility, so that's why I'm using the word fragile. So thank you. And because there's a big difference on how brittle material fails with regards to how ductile material fails. And same law, same failure theory cannot be applied to, let's say, to both of them simultaneously or kind of generally. And then the question, okay, but what is a brittle material and what is kind of a a ductile material? Well, this curve we saw here corresponds to what a ductile material, which is very much alike to the curve I showed you before in here. Kind of from the test and top, and how it just elongates before it breaks. And then ductile materials are going to have this shape in the stress-strain relationship curve of the Hooke's law. But brittle materials is going to have this shape. Basically, it's going to be very difficult to determine where is the yield because there is no yield. So a brittle material fails. When it fails, it doesn't let you know that it's going to fail. It just snaps and it breaks, and that's it. So it's something that was there and it just snapped and it just broke, and that's it. But in ductile material, which is this one, the material is going to elongate, it's going to extend, it's going to deform before it breaks. And there you have the question to the exam that I showed you. Basically, in the exam I asked, let me just pick the question, is, where is it? Okay, is it possible to know if a failed specimen is ductile or brittle by the way they fracture before they fail? These are 2-question exam. And tell you, yes, a brittle material is going to snap, and a ductile material is going to elongate, it's going to deform before it breaks. So that's it. That's the answer of that. And why this question is very important, from an engineering standpoint, because you as an engineer, if you get to work with this kind of stuff, for sure, because there are many areas now of engineering that you say, okay, and you find yourself in position of seeing specimens that failed, and you say, this is a brittle fracture. This is, well, this is a brittle material because it failed in this way, and this is a ductile material because it failed in this way, because it elongated, it deformed before it failed. And this is something important to you also because you say, well, I'm designing a machine element that is totally new. So how would I want it to fail if it's going to fail? Would I want it to deform before it fails, or would I want it just to fail as such? Of course, we don't want it to fail, but that's a valid question in that sense, because this here is going to let you know, hey, I'm elongating, I'm deforming, I'm going to fail at some point. This doesn't let you know anything. This just breaks instantaneously. So this is a very big difference between ductile and brittle material, because it depends on what you choose. You have to choose also the failure theory corresponding to that. Follow-up question to this is, okay, but what's a strain? How can I characterize or to know that something is brittle, material is brittle, and the other one is ductile? Well, here you go. I put it here for you. So if the plastic deformation before it breaks is no more than 5% of the total length of the piece, then it's considered to be a brittle material. And then if when it fails, because this has to be determined with the test specimens that you're testing, if the plastic deformation is more than 5% after it breaks, then it's considered a ductile material. So if I want to put it in graphical terms, it's something here. This is basically, I don't need to have a precise calculation here in percentage of elongation from the original one. This is obviously more than 5% of this original length. So this is a ductile material. So that's it. But the difference is that, so the way brittle and ductile materials are characterized is because brittle materials fail with less than 5% of the formation, ductile more than 5%, and that's why they have these kind of shapes here. And then all right, so but now if you have this shape here of this curve, how can I know where is the so-called maybe yield stress? Well, they have put rules that if you take 0.2% of the strain here, and you trace some parallel lines to this curve, then you can find some points of interest that you're going to be using for your calculations later. It's not as clear as this one that there is a jump in the curve, but no, you can find it also. Perfect. Now, okay, we're going to talk about types of material, and then okay, failure theories for ductile from brittle material. Okay, I know that it changed. And then if I ask you again in the exam, hey, can you tell me if there is a way to recognize that a ductile material, if the material that failed was brittle or ductile? Well, yes. By the way, it deforms. If it deforms before breaking, well, it's ductile. If it doesn't deform that much, then it's brittle. That's it. Then here it is. There are many others, but these are one of the most popular ones, and those marked with green are the ones that we're going to check here. So it's okay. If we're talking about, again, if you get an exam or get an exercise that is, hey, calculate if this is going to fail, you need to ask, okay, is this, which material is this? Well, this material, because with this material I know kind of the table commercial properties, of the material, the yield strength or something, and then I can know in the in the problem if it's ductile or brittle. So you need to know that, because depending on that, you need to choose which failure theory to use, and then that's important to know. If you don't have it, it's you're going to be assuming that thing, and that's not the purpose of this. So if it's missing, you need to ask. If it's ductile material, then there are two popular theories, that you're going to be seeing everywhere, every textbook. Is kind of the first one is the maximum shear stress theory, called Tresca, and the other one is the maximum distortion energy, which is called von Mises. Brittle, maximum principal stress or ranking, and then the other one is Morse theory. Good. So this is important to come back a little bit. So I came here, I have a loading case. This looks messy, but I have a loading case. Then I was able to populate and produce a stress tensor of it. And the reason for this was then to create the principal stresses, which are going to be used in the failure theories. That's what I wrote before. Now I'm talking about failure theories, and I totally neglected this. And why I neglected this is because we're going to be talking later, and this is something that you need to, let's say, go over with some material I just posted on in Moodle. So because this is something that you need to have to use a failure theories, but I just left this out because this is something that you need to take time to go over the material and understand. Well, you understand it already, but just expand what you have as a knowledge base. Good. We're in the failure theories, and then let's take a look at those. Because in the end, all of these failure theories just boil down to a formula. That's it. So all of these are going to propose a formula, different one in each case for sure, different formula. But they're going to propose a formula, and that formula is going to be used in your design. Let's see the maximum shear stress of Tresca. And here is where something that you might not have seen like this appears. This is the Morse circle in 3 dimension. There are 4 videos and kind of one more, for example, but there are 4 videos where all of this is explained in detail how they come up to be. All of this. So I didn't want to go over that here because it's a lot of material, a lot of time. So it's not the point. So you would have time to go over it because you're going to take what you know about Morse circle in 2 dimension and then just expand it to 3 dimension. But basically the definition, and this was one of the questions of the exam, this one here, one sentence, is what does the maximum shear stress says? It says that, it says that yielding, we're talking about ductile material, yielding means deformation, plastic deformation starts when the maximum shear stress at a point of the specimen of the part, whatever, you have to choose that point. So when the maximum shear stress of the point you are analyzing reaches the maximum shear stress at yield under any action, tension, or compression. Looks complicated maybe the first time, but it's not. And then this one you have seen, but just going over it, because now we have a 3-dimensional case. When I'm conducting a tensile or compressive test, this, when it breaks here, this yield strength here, in this point of the loading of the specimen, you're going to have a stress tensor at some point here, and that stress tensor is going to have normal stresses, and it is going to have shear stresses. Even though it is a uniaxial stress test, it's going to have a stress, right? And it says that when you find this point, and then you're going to find, then you're going to have a stress tensor. First, okay, good. I have a stress tensor. Then what you're going to find is what's the maximum, according to this, what's the maximum shear stress that you're going to find in the test. So when the maximum stress that you have in your point reaches the maximum shear stress during this test, this one here, then Tresca says your material is going to, it's not that it's going to fail, it's going to start yielding, or it's going to enter into the plastic deformation zone. So meaning that the shear stress criterion is totally based on the tensile test, meaning it comes from applying tension to a specimen. And then, this is a loading case saying, okay, well, if this is the loading case for the tensile test, at that point, then the maximum, I'll say, shear stress presented during the test is going to have it's going to be related to the principal stresses, because it's not only that, coming again here, that you have a tensor aligned beautifully with the axis, of the test. Kind of, this is the vertical axis, y, for example, and this is x. Then you're going to have these stresses here, but also that you are going to have, you don't know, these are not the maximum stresses that normal stresses that you're going to find here. You know that there is an orientation in this figure, could be whatever, I don't know which one is it for this case, where only maximum stresses are going to be presented here. Yeah, principal stresses are going to be there, and then I'm going to use this as a reference using a Morse circle. Well, that's already done. You don't have to do it in the end, because I tell you that this is going to be a formula, but kind of the origin of everything. And then I know that I'm in three dimensions, and in 3 dimensions, I'm going to have 3 values of principal stresses. I'm going to have sigma 1, which is going to be larger than sigma 2, which is going to be larger than sigma 3. And then the difference between the two extremes divided by 2 is going to be considered the maximum shear stress of that specific loading case. I say, oh, okay, so we're getting closer to a formula here. Then go over this, please, at home with confidence, but the calculation of a principal stress, even in 3 dimensions or 2 dimensions, which explained in detail in the videos I left you in Moodle, have this formula that you have known already. Kind of know that the normal stress, principal stresses equals, there is a relation between normal stresses and tau stress and shear stresses. But in the end, with all of this, if this sigma y is the strength of the material, yeah, which is represented by this one here, then what I need to make sure under the Tresca or maximum shear stress criterion is that the yield divided by 2 is less than the maximum shear stress in your point. That's it. That's all it says. Of course, there's a lot of reasoning behind this stuff. And then here I show you what happens if the loading case is totally to the positive side. What happens if the loading case falls into the negative side, and what happens if the loading case falls in between, these dividing parts. So this is the more circle representation. And then in the end, depending on the cases of if totally positive or negative or it falls in between, the Tresca or maximum shear stress is going to give you this form, meaning that if it's totally positive, you just have to take care that the stresses are not larger. The stresses for consideration are not larger than sigma 1, and that's why you have these these two possibilities here, kind of. And then if you have the negative side, you have to be worried about the value of sigma 3. That's why you have this this case here. And then what happens in between falls between those two intersection lines there. So meaning that this is in the plane, but if I try to look at it in 3 dimensions, look at this. Yeah, this is nice in the plane, but look at this in 3 dimensions, so it becomes messy. That's why in many cases you are always trying to simplify the problem to a 2-dimensional case by using symmetry, by using any other properties, but you are trying to do that. But this figure is pretty important, because if you have this figure by using the yield stress given in the commercial tables, and you draw this figure, simply said, if you calculate the principal stresses, you want to make sure that your loading case is always going to fall within this or in this region, no matter what. Tresca says that if you have a principal stresses 1, principal stress 3, and that falls within in this region, that's not going to yield, that's not going to fail. Okay. Now, well, that's it. No, basically, this is it, this one here. Then you will have time to go over this. Von Mises is based on strain energy. It's a little bit more complicated to see. You have seen this equation already, most probably in 2-dimensional case. But it says that the maximum distortion energy theory states that yielding occurs, of course, when the distortional strain energy at a point equals the distortional strain energy at yield during uniaxial tensional compression. I mean, this is also referring to the simple tensile or compressive test above mentioned. So that's the baseline to develop these theories or to propose these failure theories. This is the formula. No one misses. Please go over this. And the only thing is that you have this component here that you didn't have in the two-dimensional case, but now you're having. And again, this is comparing the principal stresses. That's why it's very important to calculate principal stresses to compare with the strength of the material. If I try to draw this here, as you know, as it was done in the Tresca theory, it says, hey, if you don't want this to fail or to reach yielding, all your points, sigma 1, combination sigma 1, sigma 3 for the planar case, and then you have also the three-dimensional case, should fall within this region. If you ask the same question for the Tresca, but in the three-dimensional case, well, your points or combination of points, sigma 1, sigma 2, and sigma 3 should fall inside of this volume here. So this big volume. So that's the answer that's the failure theory is giving to you. And this is the one. Again, it's a formula. But the reasoning behind it is pretty interesting. When we come to brittle material, this is one of the simplest one and is often used also for ductile materials, is that the maximum principal stress criterion is the same. Find me the maximum principal stress in the body that you're analyzing or designing and compare that to the maximum yield stress in the tensile test. And then this is it. Just compare the largest of these to the strength of the material, and if it's larger, it's not going to break, it's not going to yield, it's going to break, because we're talking about real material. And if you draw this, it's something like this in a two-dimensional case. So if you have sigma 1 and sigma 3 in the two-dimensional case, so be sure that whatever loading you're imposing in the body you're designing creates stresses or produces stresses that fall between this region. And that's what it says. Questions so far? Morse is a little bit more complicated, but again, it's kind of it's something that it uses, instead of using yield stress, it uses, let's say, the ultimate strength, and that ultimate strength is related to, let's go over. Okay, I'm going to take this figure, but it's not, but something like here, something in this vicinity, but of course, applied to brittle materials, it should be something that is something like in here. So it does not consider any stresses in this area, but considers stresses here. And Morse says, by the way, these are the values of the sigma 1, well, sigma 1, sigma 2, and sigma 3. Well, I don't have it here, but basically it doesn't have to be the ultimate, let's say, the stress that you are producing in your element. It doesn't have to be larger than the ultimate stress, that you have in the tensile tension there. If I compare all of these equations, all of these kind of theories, you're going to see that the most conservative failure theory to use is Tresca theory. So as answering the question of, hey, where the point should not fall so it doesn't yield or break. So if you choose this more conservative theory here, which is the Tresca, you say, well, it's very careful conditions, and which means that when you design a ductile, and this is a very important phrase. So when you design a ductile machine element using Tresca theory, definitely it's going to be larger than the ones designed with von Mises theory. So it's going to be heavier, because when you restrict so much how stresses are produced within, or what's the level of stress you are willing to withstand inside of the part, then you have to increase geometry, you have to increase size, and then that's be more weight, and sometimes weight machine elements is not desirable. So if you use Tresca compared to von Mises, it might be possible that your Tresca design is going to be larger than your von Mises design. This is a good exam question, actually. Yeah. And when you compare the brittle material, Morse theory is way permissive than the rankings shown here in the gray area. So to finalize, here what we're talking about here is just static design, meaning I have a beam and beam is loaded, and then I just determine if it's going to break or if it's going to disturb or fail. And to that end, we use this type of formula here. Yeah. So actually, let me try to. Can I copy this one? Yeah. Yeah, sometimes it takes time to respond. But this formula does not consider something very important, which is stress concentration. So you have seen also that, for example, if you are a tensile test on a piece or specimen, which is not, full, but it has a small hole in it, it's going to develop a certain level of stress that is not going to be near similar to some stress specimen that is very kind of full, or full of material kind of without this hole. And then this is where stress concentration has to be considered also in this formula here, because this is the very basic formula to get the principal stresses, but without considering any stress concentration. That does not writing really bad. Does not consider stress concentration. It's a pretty basic. But now, if you find yourself with a static case, meaning it's not moving, it's not rotating, nothing, but then it has certain disturbances in the geometry, then you have to ask yourself, okay, what are the stress concentration, or how stresses are magnified because of these imperfections in the geometry. Look at this part, for example, this very part. So this is very different here, kind of, tension. This is very nice. But when you add this kind of difference in diameter of the part and apply the same tension, you're going to have this point. And these points are caused because of stress concentration. Then, meaning that this formula has to account for stress concentration, meaning that I have to search for information about how stresses are incremented by the imperfection or the discontinuity in the geometry, so I can use it here. There is a book called Peterson. It's a very old book. I studied with this one, still very valid. Peterson's stress concentration factors. And it's kind of 500 pages of how stresses are, kind of tables like this, saying that, okay, if you have this, let's say, hole in this plate, and then the radius of the hole with respect to the width of the plate is 0.2, then you have to multiply any stress that you have by 2.5. Imagine that. So if you thought that, my stress was 300 megapascals, yeah, but if you have a stress concentration, then you have to multiply this by 2.5. So 600, and then 750, I believe so. So imagine that. Something that you don't consider. So factors. So this is a very nice picture that I got from internet. Shout out to this guy who did it. That this is the very same formula in 2D to calculate the. I didn't want to write it, so I was a little bit, say, lazy to write this one, but because you can find this in textbooks. This is the very same formula as this one here to find out the principal stresses, but they have this K here. K for the normal stresses and KT for the shear stresses, meaning that now every stress that you calculated in your stress tensor has to be multiplied by a K, a multiplier that tells you, hey, that's not the stress. Actually, you have to consider that there is an increment. Increments that can go up to 3 times. Imagine this, 3 times. Well, this is in the vicinity of 0, but here 2.8 times the value of the stress that you're estimating. So we have to be careful with this. Again, this is also, yeah, perfect. Yeah, this is within parentheses. But well, I thought it was going to be short today, but it was not. Sorry about that. But do you have any questions? What questions do you have? Or
Yes, just a short question. We will have the assignments each week, right?
Yeah.
Okay, thank you.
Yeah, no problem. All right, so that's it for today. This next week you're going to have lectures on Mondays and thank you. Monday and Wednesday. I will try to communicate with Professor Shinji or something to implement those recommendations, and take care. Take care during the weekend. Enjoy your weekend.
Thank you. Goodbye.
Okay, goodbye.